Good evening everyone, I am Strish. Thank you for joining me for this video. When you think about alkenes or unsaturated carbon-carbon bonds, there is an ability for those to accept addition reactions. We are talking here about electrophilic addition reactions, especially for alkenes. When you are looking at electrophilic addition reactions, there's something special about the carbon-carbon double bond that it can undergo this type of a addition reaction. And why is that? Let's look at that in this video. When you are considering the pi bond as behaving as a nucleophile, that's the gist of it. The pi electrons are not as strongly bound as what? As the electrons in a sigma bond. We will talk about that. Consider again the pi electrons, the electrons which are found in the pi bond, they're not as firmly fixed in place as you would see in a sigma bond. So these electrons are available for doing something. Consider also this, the pi electron cloud, which is located above or below the plane of the sigma bond. It is polarizable, therefore, because of the virtue of the flexibility of those electrons which form that pi bond, they are able to act as a base, and which means they can behave as a nucleophile, and then you can see an electrophilic addition reaction occur. We will look at that as well. These are 2 points that you must understand and notice right here before we look at the mechanism behind it. An arbitrary 2 carbons have been drawn for you. Consider the 2 electrons over here which are developed by means of sigma bonding, and you have these 2 electrons. This right here is my sigma bond, and it can be written as this. It's located within the long axis of that molecule. Here's my long axis, so the sigma bond, the 2 electrons, and you remember 2 electrons is equal to a single bond, and you represent it graphically as that. We will have here a single bond forming, and this right here is a sigma bond located along the long axis of that molecule. Therefore it's a strong bond, and these electrons are relatively fixed in place. Above and below the plane of this molecule, you'll see pi orbitals, and you have 1 electron here in each of these, which when you do the development of a second bond, which is your pi bond, it could either be above or it could be below the plane of that molecule's long axis, either above or below. You can have this representation, or focusing only on the pi bonds, you can have this representation where the 2 electrons came down here and now you have a bond. For appropriateness sake, I'm removing this one. The 2 electrons here are located above the long axis of the molecule. The pi bond is located over here. Here they're located below the axis of that, and we can just show this as well, my sigma bond right over here. Here it's located below it. Because of this flexibility, the pi bond is not as firmly fixed. It shuffles, or it fluctuates between above or below the long axis plane of that molecule. Hence this pi bond has a certain degree of laxity to it, and we will use this word laxity. You can even say flexibility, or you can even say it's loose. Because it's loose, it's not as firmly entrenched. These electrons are available for addition reactions, and we will talk about that. Understand again, the sigma bond here is fixed. These 2 electrons, you can't do much with them. The bond is strong. The pi bond is relatively weaker bond. It's located either above or it's located below the long axis, and these electrons right here, either these or these, are available for those addition reactions. This right here is the orbital mechanism that you need to understand. Sigma bonds are strong, pi bonds are not as strong. You know the valence of carbon is 4. Carbon has a valence of 4. 4 items stem off from the carbon, and the valence is met for each of these. You have over here a sigma bond, you have a pi bond. We can annotate this as our sigma bond, this right here is our pi bond. The pi bond is what's going to be undergoing those electrophilic addition reactions. If you represent this in this way, you have the sigma bond, which I'm not representing in any other way other than this line. But here my 2 electrons, which are my pi electrons. My pi electrons will form the pi bond, and you know the pi bond can be represented as a straight line, as you see over here. These electrons, because again of the laxity or the looseness as I was talking about, can behave as a nucleophile. And nucleophile means you have lone pair of electrons relatively available. They can behave as Lewis bases. That's another term you should know. A nucleophile is anything which behaves as a Lewis base. What's a Lewis base? It's an electron pair donor, not an electron pair acceptor, in which case that's a Lewis acid. This right here is an electron pair donor. The pi bond or the pi electrons of an alkene, which is a compound that has carbon double bonds, and alkene has pi electrons. Those pi electrons are nucleophilic. They behave as Lewis bases. Let's see how this electrophilic addition reaction occurs. You have an alkene here behaving as a nucleophile, but the reaction is called electrophilic, and I'll tell you why momentarily. You have a certain hydrogen halide, HX. You know where X can be chlorine, it can be bromine, and can be iodine. We won't put fluorine here because the HF bond is strong. The fluorine is very electronegative, and it doesn't behave as well, nor does it ionize. In solution form, you're really looking at what? Not HX, it has ionized. You're looking at H plus and you're looking at X minus, like a chloride, bromide, iodide. Here you have hydrogen ion. These electrons are going to seek, because they're nucleophilic, they're going to look for this item right here, which is an electrophile. It's going to look for that. And when it does, you're going to see an addition reaction come into play. You have this hydrogen added right over here, and you have a carbocation over here. What does this carbocation represent? A charge deficiency. And this right here does not indicate any charge deficiency, because if you look at the octet of each of these carbons, it's met. You have 1, 2, 3, 4, 5, 6, 7, 8. You have 1, 2, 3, 4, 5, 6, 7, 8, because each line represents 2 electrons. These 2 electrons are being shared with each carbon. Hence you can use it, double count them. You can do 2 over here, then you can do 2 over here. The 8 electron octet is met. The octet is met for each. This hydrogen has been pulled over here. Now we have a carbocation here, which means a charge deficiency. What will come over here? It's this. And how can you represent this in a better way in terms of Lewis structure? Like this. You have all electrons over here, and it's this. It's gonna now attack over here, and you'll have your addition reaction. You have the hydrogen coming over here, and now you have the halogen atom coming over here, and we have an electrophilic addition reaction which has been completed. It's called an electrophilic addition reaction because your alkene, the pi electrons from the pi bond, behave as a nucleophile, and they seek out an electrophile, and that electrophile is added onto your compound, generating what is called a carbocation, which is then seeked out by another nucleophile in your reaction medium, and it adds over there. It's electrophilic addition because an electrophile is being added onto your compound, the electrophile here being a hydrogen. But the electrophile can be something other than a hydrogen, doesn't necessarily have to be that. We're just using that here in this example. Let's look at another reaction. That'll be the end of this video. Keep in mind this very important fact. When you're doing an electrophilic addition reaction on an alkene, an existing pi bond becomes converted into a sigma bond, and we can just show you one more reaction. We're looking at a compound which is a cyclohexene. You have this right here, double bond, and it is being reacted in the presence of hydrogen chloride, gaseous hydrogen chloride, so it will exist as H plus and Cl minus, hydrogen ion and chloride anion. This bond here, which is really made up of 2 electrons, and I'm going to change it to this right here, 2 electrons, they're going to seek out an electrophile and they will add it. When you are going to add it, what will happen? This is what will happen. You have over here the hydrogen added here, and now we have a charge deficiency here. And keep in mind the valence of this compound, if you show it normally is this, you would have had a hydrogen here and a hydrogen here. And I'll show you the other hydrogen here just for completeness sake, because the valence of 4 is met. You have 1, 2, 3, 4, 1, 2, 3, 4, valence of 4, and you have 1, 2, 3, 4, here you have 1, 2, 3, and here you're missing that. What will add over there? This. The chloride will add right over here and complete the valence of that carbon. And your end result will be this. You're going from what was a pi bond to what will be a sigma bond. Here's your one sigma bond, here's your hydrogen, and here's your other hydrogen, and here's your chlorine, and your other sigma bond has been developed. You have essentially converted one pi bond into 2 sigma bonds. One is this, carbon and hydrogen, one is this, carbon and chlorine. You have generated 2 sigma bonds. This compound right here is cyclohexene, because you have an alkene in a cyclohexane ring, and this right here would be what? Cyclohexane with the chlorine on position carbon 1. We will call this 1-chloro-cyclohexane, and it's right. You've gone from an alkene to an alkane. You've gone here from an ene. Ene is an alkene designation to an ane, which is an alkane designation, but you have done an electrophilic addition reaction. HCl, hydrogen and chlorine have been added on either sides of your double bond, as you can see. This right here is it. pi bond behaves as a nucleophile because the two electrons which form the pi bond are relatively loose and they are able to behave in a nucleophilic manner, meaning as Lewis base, and search out for an electrophile, and then the other nucleophile which is present in your reaction medium is able to complete the valence of your opposing carbon atom. Thank you for watching.